In this video, we shall see the working of clamping circuits. Let us see the basics of clamping circuits here. So let us consider a capacitor C connected to a voltage source of 2 volts. So assume that this terminal is open circuited. Now, what is this capacitor voltage now? So as we know that onto the left hand side of this capacitor parallel plate, so we are applying a positive charge. So we are supposed to get in order for this capacitor to charge for a voltage, these negative charges have to accumulate on the right hand side of the capacitor plate. Now since this is an open circuit, so the charge across the capacitor will not build because this is not getting the electrons because it is open circuit. Meaning if we are connecting a capacitor one end to this 2 volts and if the other end is floating, actually the capacitor voltage is 0. So capacitor will not at all charge to any voltage. So there is no charge accumulated onto the capacitor. On this side we have plus, on this side nothing will be get accumulated. So the capacitor will not the capacitor voltage will be 0. The same thing is true even if I apply a sine wave. So if I'm applying a sine wave here, so as we know that as the positive voltages are as the positive voltage is increasing onto the left hand side of this parallel plate capacitor, onto the right hand side we are supposed to get the negative charges. So since we don't have the source for getting these negative charges, this capacitor voltage will be 0. Actually the output voltage is equal to the input voltage minus the capacitor voltage. If you write the KVL for this, the output voltage is actually equal to the input voltage because that is nothing is stored here. So V0 is equal to V2. So the same thing is true here also. The output voltage is exactly equal to 2 volts because there is no charge stored in this capacitor. Now this is the basic of the clamping circuit. If you have a capacitor, if one end is not connected, the capacitor will not be charging at all. Now let us consider the actual circuit. Now let us have a diode connected onto the on the right hand side of this capacitor parallel plate. Now what happens here? But assume that we are applying a sine wave onto the left hand side plate of this capacitor. So as the voltages keep on increasing, now we know that the plus is keep on building on the left hand side of the parallel plate capacitor. On the right hand side we are supposed to get the negative charges. So where is the path for this negative charges to reach this side of the plate is because only diode is connected to this ground and ground is interconnected to the supply here. Now there is a possibility of this getting the negative charge through this, meaning if this diode gives the negative charge, so it's actually becoming positive over here. Diode happily gives this negative charge because this will be turned on. So usually during the positive half cycle, you can see here, so as the input voltage increases, so the voltage on the left hand side of this plate is keep on increasing. On the right hand side the negative charges will be get accumulated because this diode is on. Now you can see this is the capacitor voltage, this is the input voltage, this is the capacitor voltage. So capacitor voltages keep on building here. So now you can see capacitor voltage will be charged till the peak voltage. So meaning, so the required negative charges onto the right hand side of this parallel plate capacitor is being provided with this, because once this gives the negative charge, so this is plus here, so this plus is required to turn on this diode. So this diode is turned on so that capacitor charges up to the peak voltage. Now from 0 to T1 the diode is on now, so diode will be on. So what happens if the input voltage starts reducing? So as the input voltage starts reducing, the positive charges on the left hand side start reducing. So now this has to push these negative charges onto this diode. So once you start pushing these negative charges, this diode turns off. Now you can see if this is losing, this capacitor voltage would have reduced. Now only path for this capacitor discharge is through the diode. If the diode is off during this T1 onwards, since the diode is off, so this is not at all discharging. Now you can see this capacitor voltage is holding the charge Vp for any time after T1. Now since the diode is off here, so this is going to stay there for ever. So as long as you are not providing any more resistance path for this capacitor discharge, this stays at whatever the value that it has stored up to, that is Vp. Now let us have a look at, okay, how does this output voltage looks like. As you know that output voltage given by the KVL, it is V input minus the capacitor voltage. And let us just simply try to get what is the plot for our V0. This is the V0 plot. Now you can see this is starting from 0 time. So the input voltage is increasing, the capacitor voltage also keep on increasing. Actually the output voltage is V in minus the capacitor voltage. So it is V in minus this. As you can see, both the shapes are exactly same. So this minus this happens to be 0. Meaning the capacitor voltage is charging from 0 to T1. The output voltage is actually 0. Now anything after T1, so the capacitor voltage stays at Vp, that is the peak voltage. Now if you actually find out what is the output voltage, because the output voltage is nothing but input minus the capacitor voltage, which is Vp. Now you can see this is 0 here. So now the voltage is Vp minus Vd on. Now this Vp is reducing. Assume that Vp is 10. This is 10. So 10 minus 10 is 0. Now it is, assume that it is 9. So this is 10. So 9 minus 10 is now minus 1. Assume that this is now minus 10. So what is minus 10? So this is minus 10 and minus of another 10. So it will be minus 20. Meaning, so as the input voltage varies beyond T1, the output voltage is actually going negative. So this is how the output voltage is always below 0. And if you can carefully observe, the peak to peak of this is Vp and this is minus Vp. The peak to peak is 2 Vp. The 2 Vp still remains here. Now this is what happens. This is how it looks when the time is starting from 0 and under steady state. So the capacitor voltage is staying at Vp. So under steady state, okay, in steady state, that is once that capacitor voltage charged to Vp, we call it as steady state. Okay, in this case, any time after T1, it we call it as a steady state. Now you can see capacitor voltage is equal to Vp. Now this is the input voltage and the steady state. Now this is now T equal to 0. So T is elapsed somewhere here. Now as the input voltage increases, the output voltage is also increasing. But carefully you can see the input is 0 here, whereas the output 0 is here. So you can carefully observe, this is a positive peak of the input. This is a positive peak of the output. If the positive peak of the input is 10 volt, you can see where the positive peak of the output is there. So positive peak of the output voltage is climbed to 0 volt. Meaning in this circuit we are actually clamping the positive peak of the input voltage which is there at Vp to 0 volt. Now you can see this is now the input waveform is now clamped such that the positive peak is now clamped to 0. I can see this is your positive peak which is now clamped to 0 volt. So that's what is given here. It is positive peak clamped to 0 volt. Now we shall do the simulation of the same and then try to verify how it looks like. Now in this case we assume that VD1 is equal to 0. If VD1 is not 0, if it is something like 0.6 volts, now instead of clamping the positive peak to 0, it will be clamped to some V gamma, that is 0.6 volts. So let us have a look at the similar circuit in LT-Spice. In the LT-Spice we are connecting the resistor here, because this resistor may provide a discharge for this capacitor to discharge when the diode is off. So there is no much variation in the output waveform if the diode is there or not. So as long as the resistor is of a very high value, so this capacitor voltage is going to remain at the peak voltage. So we shall have a look at the simulation. Now this is the waveforms. Let us have a look at the circuit. Now this is the circuit what we have similar to that. Now here we have a 100k resistor. So this 100k resistor is actually providing a discharge path for this capacitor. So once the capacitor is charged to Vp, so this diode will be off. The capacitor can discharge to this resistor through 100k, which is a 100k resistor. Since the value of resistor is 100k and the frequency is taken as 1 kHz, so let us have a look at, okay, how does the waveform looks like. If I run this, now let us see. So as you can see, now this is the input voltage, which is a sine waveform of 10 volt peak, the green one. The output is the blue one. You can see now this is the positive peak here. This is the positive peak of the input. If you actually carefully see the positive peak of the output, which is the blue one, now it is now clamped to 637 millivolts, meaning the positive peak is now clamped to V gamma. So because in the previous thing we saw that this is the positive peak, it was clamped to 0 because VD on is 0. If VD on is not 0, so this will be clamped to that V gamma. So that's what is happening here. So it is now clamped to V gamma. Now carefully observe this red line. So red line is the capacitor voltage across the capacitor. Now I can see the capacitor voltage is initially building up. And just have a look at this. I can see the capacitor voltage is initially 0. So it will be 0 till the diode is on. I can see as the diode turns on, the capacitor voltage keep building. So capacitor is going to charge up to Vp if the VD on is 0. Since VD on is 0.6, it will charge to Vp minus VD on. Now we can see it is staying there. So the capacitor voltage is staying. So if we just go back and see what happens to this capacitor voltage, I can see capacitor voltage is remaining constant. Capacitor voltage is remaining constant. Now let us have a look at what is this this current. This is the current plot. If you can actually have a look at this. Now this is the current through the diode. Now initially the current is 0 because the input voltage is less than V gamma. As soon as the input voltage exceeds V gamma, so there is a spike in the current. So current increases, shoots up. Now the current is again reducing. So why the current is reducing is because once the voltage is more than V gamma, the capacitor starts charging. So as the capacitor voltage is charging, the voltage across the diode is keep reducing. So a stage will reach where the diode turns off. So diode will turn off when the capacitor charges to Vp minus Vd on. So at the peak, at the positive peak of the input voltage, actually the capacitor voltage is going to become Vp minus Vd on. At that time your diode stops conducting. Now you can see diode current is 0 here. Now this is the current corresponding to diode. Now it has reached 0 current. Now you can see this is almost nano amperes, which is now the diode is off, meaning the diode will be on only during the first quarter of the first half cycle. So that's why between 0 to Vp the diode is on. Once the diode is on, so as long as the diode is on, this capacitor will be charged to Vp minus Vd on or Vp if Vd on is 0. Now this will be charged to that peak voltage. So once it is charged, the diode turns off. So now the capacitor voltage charged to Vp, as we just saw in the this steady state case. So now the capacitor voltage is equal to Vp. So under steady state, the positive peak is now clamped to 0 here if Vd on is 0. If Vd on is 0.6, now it is clamped to 0.6. So that's what we saw in this. Suppose if I simulate this and if I start saving the data after some time, that is, let me just say it as let me see it after 1 millisecond. So this is like seeing the waveform in the steady state. Now I can see I'm not at all. Okay, let me just take out this current graph, which is not of very much important now. Let me just take out this. Can you see now? This is the capacitor voltage. Is it constant now? So now it is constant. Now the capacitor is charged to Vp minus Vd on, which is 10 minus 0.63, which is 9.37. The capacitor voltage is constant. So why capacitor voltage is constant is because we have a resistor which is of very high resistance. Now it is not allowing it to discharge. Suppose if you reduce this resistance to 1k, you can see. So during the discharge period, the capacitor, I can see the capacitor voltage reducing. Can you see now? This is the capacitor voltage reducing. So in case of clamping circuits, we have to have a resistor of very large value so that it doesn't allow the resistor to discharge too much. Now you can see now it is remaining constant. So this is how we can understand the working of this clamping circuit. Now this clamping circuit you can have in series with the diode a reference voltage in plus or minus battery, so that this will be clamped to different voltages. Those things we'll see in the next video.